This flowchart shows how a compiler translates code into machine action. We start with a grammar, derive a sequence, build a parse tree, and arrive at a definitive meaning. For this pipeline to function, every program must yield exactly one specific meaning. Without this structural certainty, a computer cannot reliably execute instructions. If the translation isn't one-to-one, the output becomes unpredictable. Take the English sentence, "I saw the man with a telescope." The phrasing implies two different scenarios. Did you use a telescope to see the man, or did the man you saw happen to be carrying a telescope? Humans handle this linguistic overlap effortlessly. We use surrounding context to pick the correct interpretation without thinking about it. But a compiler operates without context. If you feed it a simple mathematical string like a plus b times c, humans assume multiplication happens first. The compiler doesn't have that intuition. It follows the literal rules of the grammar it is given, regardless of mathematical convention. This is a standard context-free grammar designed for basic math. At a glance, the rules seem capable of parsing variables joined by addition and multiplication. To test these rules, we use a specific mathematical string as a stress test, ID plus ID times ID. By tracing the execution path for this string, we can determine if these rules lead to a single result or a logical conflict. This syntax tree shows the first potential path. Following the grammar rules, the compiler builds a structure that prioritizes the multiplication step. If our variables are 2, 3, and 4, this structure evaluates as 2 plus 12, which resolves to 20. Now we restart the test with the same string. Because the grammar is broadly written, the compiler can legally build a second, different path, this one prioritizing the addition. In this version, the math evaluates as 5 times 4, resulting in 14. One valid string has generated two different architectures and two different outputs. Because the machine cannot choose between them, the language is unreliable. This is the formal definition of an ambiguous grammar, any grammar where at least one string generates multiple distinct parse trees. A grammar isn't judged by the strings it handles correctly. If even one string is ambiguous, the grammar itself is considered flawed for compiler design. The problem lies in the rules. This grammar places addition and multiplication on the same hierarchical level. To fix this, designers must introduce operator precedence. They have to encode the hierarchy of math directly into the grammar rules, rather than assuming the machine knows the order of operations. Looking back at our pipeline, we can see the point of failure. The path diverges at the parse tree stage, creating competing interpretations from a single input. This means the same source code can produce different machine instructions, leading to inconsistent outputs across different systems. To ensure predictable execution, compiler architects must design unambiguous grammars. The goal is a mathematical structure where every rule points to exactly one intended meaning.